Continuing on physical chemistry, we're now beginning on chapter 4 with section 1. Now, material equilibrium has two parts. The first is reaction equilibrium. Let's say that we have chemical species 1 in equilibrium with chemical species 2. Remember, arrows going both ways about the same size means you're at equilibrium. Now, an example would be NO2 gas, 2NO2 gas, which looks brown, in equilibrium with N2O2 gas, which is a dimer of this stuff and is colorless. So what happens then, that's an example of reaction equilibrium. Another possibility, that doesn't make any sense. This isn't balanced. I need to look into this one here. Okay, the alternative, another type of material equilibrium is phase equilibrium. Let's say that we have silver chloride, which is solid, in equilibrium with aqueous silver plus ions and aqueous chloride ions. So we have a test tube here. The silver chloride solid is going to sink to the bottom, and then we have the silver plus ions and the chlorine minus aqueous ions all up here, and then of course air, etc. up here. So now we're going to talk about two new state functions. Capital A, not to be confused with area of course, is called the Helmholtz free energy function. And A is defined as U minus Ts. Now that we've defined entropy, we can use it. Now the Gibbs, capital G for Gibbs, is the Gibbs free energy function. G is defined as H minus Ts. Now, chemical potential mu, not to be confused with the Joule coefficient, of course, is closely related to capital G. We'll show later on exactly what is the relationship between mu and the Gibbs free energy. Now, the natural variables of U are temperature and volume. So the natural variables of the Helmholtz free energy are temperature and volume, and the natural variables of the Gibbs free energy is temperature and pressure. Okay, continuing on physical chemistry, chapter 4, we're doing section 2 now. So let's say we have a non-equilibrium system. Now first, let's say we have no phase equilibrium. We have mechanical equilibrium and thermal equilibrium though. So here's our system. We have some sort of frictionless partition here. This is like a big cylinder here. So we have a piston here with pressure P this way. We have a piston here with pressure P this way. We have adiabatic walls. We have sodium chloride aqueous over here, but it's unsaturated, which means we could dissolve even more salt if given the chance. And then over here, we just have pure salt, NaCl, no water. Now, work is equal to 0 just for removing the partition. Now remember, U is a type of energy. It's the internal energy, and it's extensive. Now, mu sub I is the internal energy of the system. So mu sub I is going to be, or not mu, U. The internal energy I is going to be equal to the internal energy of the solution plus the internal energy of the sodium chloride. You can just add them up because it's extensive. We'll call that 1 for now. Now the entropy of I, that's going to be the entropy of the solution plus the entropy of the salt. And again, you can just add those up because entropy is extensive. Now, like I said, we're going to remove the partition. We're going to do that adiabatically, so Q is equal to 0. And we're going to do it reversibly, so work is equal to 0. It doesn't take any force to just remove the partition. Now, what's about our final state? The internal energy of the final state is going to be the internal energy of the solution plus the internal energy of the sodium chloride, salt. We'll call that equation 2. And the entropy final is also going to be the entropy of the solution plus the entropy of the sodium chloride. Now this is true at any time, not just at equilibrium. Now, let's say we have no equilibrium reaction. So we have H2 gas plus O2 gas gives us H2O. This is probably vapor also, with no catalyst, so there's no reaction. Normally, if you just have hydrogen and oxygen, until you light it with a match or something, it's not going to actually burn. We'll talk about why, later on. So we're at moderate temperature, constant pressure. So there will be entropy of mixing, a change in entropy just from mixing because of the second law of thermodynamics. And there will be a change in internal energy of mixing just from the first law, because these are not ideal gases, remember. They have intermolecular forces and so on. So what if there's no thermal equilibrium? Let's say we have some rod, a metal rod that will conduct heat. And we have temperature 2 over here, temperature 1 over here, with temperature 2 greater than temperature 1. Well, to analyze this, we can just slice it into infinitesimal slices. So we have entropy of slice 1, and the internal energy of slice 1, entropy of slice 2, and the internal energy of slice 2, entropy of slice 3, internal energy of slice 3, blah, 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 all the way to infinity if it's really continuous, or towards infinity. So the entropy is just going to be entropy of slice 1 plus entropy of slice 2 plus the entropy of slice 3, etc., all the way to whatever n is the number of slices. So the entropy of slice n. And of course you just add that up like that because of entropy is extensive. And then same thing, the total energy, internal energy U is going to be the internal energy of slice 1, internal energy of slice 2 plus internal energy of slice 3, etc., all the way to internal energy of slice n. So for all systems not in material or thermal equilibrium, we can still assign values for internal energy and entropy. That's all for section 2. Now we're on physical chemistry, chapter 4, section 3. We're going to talk about entropy versus equilibrium. Let's say we have an isolated system, but it's not in material equilibrium. So here's our system. We've got some stuff down here. You notice there's like 2 different phases or something, but we have 3 arrows up and 1 arrow down. So it's not an equilibrium. We have a net something going on here. So the dotted line shows that it's not in material equilibrium. It could be phase equilibrium or reaction equilibrium. It doesn't matter. And it can do positive or negative work. It can do positive or negative heat. So the criterion for material equilibrium in an isolated system is the maximization of the system's entropy S. Now let's say we have a closed system that's not in material equilibrium. So here's our system. It looks exactly like before, but since it's just closed, not isolated, energy can still get in and out. So we're at thermal and mechanical equilibrium still, but we have this adiabatic impermeable wall outside of our surroundings there. So we can have work in or out, and we can have Q in or out. So basically we can have energy transfers of various types. But remember, closed systems means this wall here is impermeable. There's no transfer of matter. So the criterion for material equilibrium in a closed system is the maximization of the total entropy. The total entropy is equal to the entropy of the system plus the entropy of the surroundings. But here's the problem. We might not know anything about our surroundings. How are we going to keep track of the entropy of the surroundings? We know our system, but we don't really know what's outside necessarily. Now, we're always, because we're doing reversible processes mostly, we're always going to assume that the surroundings are in thermal, mechanical, and material equilibrium. So let's say that the dq of the system flow into the system. So it's going to be an endothermic reaction. Energy is going into our system. Then that means, well, dq surroundings is equal to minus the dq of the system by conservation of energy. So the dq of the surroundings plus the dq of the system has got to be equal to 0. Since the system is not in material equilibrium, we have an irreversible process. Therefore, the ds of the universe, the differential of the entropy of the universe, is equal to the differential of the entropy of the system plus the differential energy of the surroundings is greater than 0. Because it's irreversible. Now, ds of the surroundings is going to be dq of the surroundings divided by temperature, since we're just assuming that the surroundings are in equilibrium. Because the surroundings are so big compared to our systems anyway, it's not like we're going to affect it or something. Now, ds of the system, the differential of entropy of the system, is not equal to dq of the system divided by temperature, because our system is not in equilibrium, so it's not reversible, so the formula wouldn't apply. In fact, we know that ds of the system is greater than the minus ds of the surroundings because this is reversible and this is irreversible. But we know that the differential of the entropy of the surroundings is going to be minus the differential of the surroundings divided by temperature, which has to be equal to the differential of the Q of the system divided by temperature. So equation 1 here, we're going to refer back to, is going to be the differential of the entropy of the system is greater than the differential of the heat of the system divided by temperature. Now this is true for a closed system that's not in material equilibrium, but it is in thermal and mechanical equilibrium. Now equation 2 will say ds is equal to dq of the system reversible over T. Notice the equal sign, therefore reversible. This is when you're at material equilibrium. So we have dq of the system is equal to dq irreversible. So we're going to combine equations 1 and 2. We're going to say ds is greater than or equal to dq over T. Now the system is implied if we don't specify it. Now this is for material change, but a closed system in thermal equilibrium and mechanical equilibrium. So remember, if the equal sign is when it's material equilibrium, which means it's reversible. The greater sign is before we reach equilibrium, which means it's doing irreversible process. It could be irreversible phase change or chemical reaction or whatever, because we're talking about a material change. Material change means phase change or chemical reaction. So that means that the differential of Q is less than or equal to T ds. So the first law, remember, said dq is equal to u minus dw, which therefore is less than or equal to T ds. So du is less than or equal to T ds plus dw. This is true for a closed system, mechanical and thermal equilibrium, but undergoing a material change. And that's the end of section 3.